So what I said, the fundamental problem of the algebra was you have to solve the system of homogeneous linear equations. So that is ax plus b. And in that, what was this a? Let's again write these equations. This was like 2x plus 3y plus 4z, let's suppose, is equal to 1. Then we'll have another equation, 1x plus 2y plus 1z is equal to 6. 6x plus y plus 14z is equal to, let's suppose, 8. This was our system of equations. If you see, if you again go back, so what were these equations basically? So these were called as linear equations mathematically because these variables, they have power of 1, they are raised to power 1. So if you see the geometrically, they represent some linear surface, so they represent linear surface. So in the case of line, if we have two lines, so basically we represent them like this. So if you have a line like this, if you have another line like this, so this was the solution, the point of intersection. We told that this is the solution of these two lines where they intersect. So I told you that in the similar way we have in 3D we have planes. Okay, beyond this 2D and 3D we cannot basically visualize things. So but algebra gives the tools by the help of which you can solve these equations. So now we wrote in a succinct way. We just took these coefficients out, these coefficients that were here, and we made them what's called as coefficient matrix A. Then we took this x out of these, so which represent x, y, and z, and then we took this b, that is 1, 6, and 8. This is how. And now we are trying to find the values of x for which the system of equations has a solution. तो हमारे पास जो चीजें थी, तो we want to find the values of x, so that when we put these values into this equation, when we put the value of x, value of y, value of z into these equations, they should be satisfied simultaneously. That's what we want to find. So that was the fundamental problem that algebra solves. Okay, so in order to solve this problem, what I told you is that we'll sort of break up this problem into two things. So we'll say ax is equal to 0 and ax is equal to b. And we'll first try to find all these values of x for which these equations become 0. I'll try to find the value x, y, and z such that this is equal to 0. I'll try to find the values for this such that these equations become 0. That's what I wanted to do. All these numbers which satisfy this equation, where we'll put these numbers, because they can be, for example, 0, 0, 0 is a simple solution which will when we multiply this a, and it will give 0. That's one of the vector. Some other vectors can be there, 1, 2, minus 3, and some other vectors can be there. So this is a set of vectors. So this set of vectors, I called it as null space. Null space. So null space basically was the set of vectors which takes this matrix equal to 0. Like when we substitute these values, it makes that system of homogeneous equations equal to 0. And we call it a special solution. Special solution. Okay. So how do we find this special solution? Now if we have this ax is equal to 0, how to find this null space? How to find the values in null space? So the basic algorithm that we followed is, the first step in the algorithm was, we'll reduce it into row reduce echelon form. So how did it look? So we had a matrix like this. We tried to make it like this. For example, we'll have an identity element here and an identity element here. Then we'll have some values f, then maybe zeros or something like this, if only. So there will be some identity like 0, 1, 0, 1, and then 2, 3, something like this, or maybe 0, 0 is followed by here. So I tried to reduce it into row reduced echelon form by using the elementary transformations, and from that I got these variables. So when I'm trying to reduce it into row reduced echelon form, so I had two types of columns. Now I have two types of columns. So one type of column was pivot columns, and one type of column were free columns. So in the pivot columns, what we had is, so I told you if this is A, B, C, D, E, F, G, H, I, J, K, L. So this is the first pivot entry that we had. So why is it called a pivot? Because I want to make all the entries below it 0. So because I'm using this. And now in the next iteration, what I'll do is, I'll take this f and I'll make all the entries below it 0. Okay. In a similar fashion, I'll do with, if it's a bigger matrix, I'll do accordingly. So what I'm saying, sometimes while you are performing these row operation, where we are performing these elementary transformation, elementary operations, so what happens, these pivots become 0. Sometimes this may become 0. Okay. So now the pivot is gone. Now the one pivot is gone. So what I'm saying is, wherever the pivots are left after you reduce the equation to row reduced echelon form, we'll tell them they are called as pivot columns. So let's suppose this pivot remained, and let's suppose this pivot remained. Let's suppose this became 0. Now we have these two pivot columns, and now the other two columns are called as free columns. This and this are called as free columns. So these were our pivot columns, and these were our free columns. So in order to find the solution, what we did is, now we had a, let's suppose this x1, x2, x1, x2, x3, and x4. That was actually here. So x1, x2, x3, and x4. So we wanted to find values for these. So what I'm telling you is that this is a pivot column. This is again a pivot column. Now we have these free columns also. So in order to find the null space, what I will be doing is, I'll give some random values to these free columns, and I'll get values for this x1 and x3. Okay, let's suppose what random values will I give. I particularly chose 1, 0 and 0, 1. So what I did is, for these free columns I gave the values 1, 0. Then let's suppose these values came out to be a and b, and because we are solving the equations, we will put the values of these x3 and x4 back in the equations, because these are free variables. And for the free variables, we are assigning 1, 0 in the first iteration, and we got a and b, let's suppose, or a1, b1. And the next time I'll be giving, as we have only two free columns here, so in the next iteration let's give them 0, 1 value. Okay, now we can compute the other columns, other values for the pivot variable. So we had, let's suppose, a2 and b2. So now I told you that this equation sort of solves this ax is equal to 0. So if you put these values instead of these x's, so you will get ax is equal to 0. This vector will satisfy the equation ax is equal to 0. Again, if you do the similar thing with this, so this will also satisfy. So you can say that if you take any scalar vector of if you just scale this vector, so this basically is a vector. If you now scale it by a factor of c, or let's suppose by a factor of capital A, so you again know that this will again take this equation to 0. This also will be the solution to this equation. Similarly, if you scale this vector with b, so scale vector also will be the solution of this. And now if you take linear combination of these two things, it still will be the solution of this equation. So now this is basically what we call as a special solution. And this is the null space. This is null space of our vector, our matrix A. So let's I'll represent A dash and B dash coefficients. So null space of A are the combination of these two vectors. So let's suppose if we have, and the matrix, just for the solution sake, we had A, B, C, D, E, F. Let's say A1, A2, B, C1, something like this. Some entries were there. And in here we had 1 and 2 pivot rows, and we had, let's suppose, 3 free variables. These are free columns. Okay, so now we have 3 free variables or 3 free columns, because one column represents a variable, because for it's x1, x2, x3, x4, and x5. So whole of this will get multiplied with this. Okay, and whole of x2 will get multiplied this with this whole column. So we have 3 free variables, and we have 2 pivot variables or 2 pivot columns. So what I'll do is, again, I'll assign these free variables. Initially I'll assign it 1, 0, 0. Next time I'll assign them 0, 1, 0. Next time I'll assign them 0, 1, 1. And now I'll get the values for the other value. Let's suppose in here these were our 3 free variables. Let's suppose. Okay, let's suppose these were our free variables. So I'm just erasing it. These 2 were our pivot variables, and the 3 were our free variables. So in the first iteration I'll give them the values 1, 0, 0. Okay, now out of this I'll get some values. So I'll get some values for x1 and x2. Let's suppose they are a1, b1. In the similar way, I'll give 0, 1, 0. Now it will become a2, b2. I'm just giving a general framework. 0, 0, 1. Now it will become a3, b3. So these 3 will be the solutions to the equation ax is equal to b, x is equal to 0. So what I'm telling you is that if you take this vector, so it is the solution of this equation. Now if you multiply it with any coefficient, let's suppose we call that c1, it'll still be the it'll still satisfy this equation. Okay, because I told you that if ax is equal to 0, so if you multiply c1 on the both sides, it will become c1 ax is equal to 0. That will be a c1x is equal to 0. So still it will satisfy this equation if I am just multiplying this whole vector by c1. Similarly, if I am multiplying this vector by c2, still it will satisfy this equation. Similarly for this c3. Now I'm saying if I take the linear combination of these 3 vectors, okay, they'll still be in this null space. So these are all the possible values in the null space. So is this clear how to solve this Ax is equal to 0 now? Is it clear?
Yes, sir.
Okay, then we try
Yes,
to
sir.
find the special solution. So we try to find the which said like we had to find Ax is equal to b. What we did is we first found Ax is equal to 0. Now we found the solution, how to find this null space basically. Null space of A is now all the vectors which basically satisfy this equation, or which when multiplied with this A and takes this to 0. Now the other thing that we were to solve is that Axp is equal to b. So we want to find a particular solution. How to find the particular solution? Again, by reducing it to row reduced echelon form, and then setting up b, let's suppose some values b1, b2, b3, and we'll find one particular solution. Let's suppose that solution was a1, b1, c1, d1, something like this. That was our particular solution. In order to find how to find the solution, watch the previous video. And then we said the complete solution is this particular solution plus this special solution. Okay, this special solution is basically the null space. Okay, now you cannot basically multiply this with any. You cannot take combination of this. You cannot take the combination of special solution. Why? Because this equation is Ax is equal to b. If you multiply it with some constant, let's suppose c. So if you multiply it over here c, so now you are not finding the solution. You are finding the solution to cb. So initially we had Ax is equal to 0. If you multiply it with c, so c multiplied by 0 is also 0. So it was equivalent to finding the solution of Ax is equal to 0 also. So that's the reason we are not multiplying this xp with any coefficient. But in this null space, we are multiplying by the coefficients. If you see it over here, so we are multiplying with the coefficients. That's the reason why are we multiplying with the coefficients as well. Is this clear now? How to find this complete solutions?
Yes, sir.
Okay. Now after that, we try to define what is a rank. So with rank, I meant that the number of pivot columns can be defined as rank. So now you saw that when we reduce this matrix into a row reduced echelon form, we got some pivot columns. So the number of those columns is equal to the rank of the matrix, or is equal to the rank of those equations. So if I am just talking in terms of the equation. So we had this A, we had this X, and we had this B. So first thing, we defined the rank onto this matrix, on this coefficient matrix. So rank was defined the number of pivot columns that were left after we performed this element transform and we got row reduced echelon form. That was the rank. Now I told you that A, let's suppose, is a matrix which has m rows and n columns. This is our matrix. So as I'm saying you, rank is defined as the number of pivot columns. So this rank will be less than or equal to n, because this is the number of columns. So because at most the rank can be n, because if all the columns are pivot columns. So other than this, so it can be less than or equal to n. So this is the first condition in the rank. So because we are taking these pivot entries from the rows itself. So these entries, if you see, we took this entry and the second entry, then third, and like this, corresponding to the rows. So this again sort of puts a constraint on this rank. So this rank can be less than or equal to m. That is, maximum rank can be m, because now we are constrained by the number of rows as well. Okay. Now what I'm saying is that I established from these two things, I established a fact that this rank is either less than or equal to minimum of this n comma m. So whoever is the minimum value among these, so rank can be at most that value or either less than that. So this is what I established from this. So rank can be less than or equal to n comma m. Is it clear? Was it clear till this point?
Yes, sir.
Riyan, are you understanding? Salim?
Yes, sir.
Nice. So now what I said is that let's take a matrix whose rank is n. So we had a matrix A, m rows, n columns. So I'm saying rank is equal to n. If rank is equal to n, that means every column is a pivot column now. Every column in this matrix is a pivot column. So every column is a pivot column. I am trying to find the null space of A. So I am trying to find the Ax is equal to B. I am trying to find the values of all the x's for which this matrix becomes 0. So I asked you a question, what can you tell me about this? So let me answer that question myself, because you haven't revised the lecture. So what I'm saying is that if Ax is equal to 0 and the rank is equal to null, rank is equal to n, that means we have no free variables. That means we have no free variables. If you do not have a free variable, so you cannot assign any random value to these values and find this equation. So I can say that for that particular thing, we can say that we have no variables. So there is this null space of A becomes only 0, 0, 0 vectors. So because you have no free variables, so you are left with giving like free variables are nothing, so you have to give them zeros, and then you have to find the values for x1, x2 up till xn. Let's suppose we are solving n equations. So we can claim that if if all the rows are pivot rows, okay, r is equal to n, we call it a full column rank matrix. Okay, all the columns are involved in this pivot, all the columns are involved in contributing towards the rank. That means this null space of a now becomes 0. Can you argue why? So because we don't have free variables. So if you see how we computed this null space now, we gave some values to the free variable, then we got some values for this pivot variables. Now we don't have free variables to give values to. Now there will be some values to this, and we cannot solve it. Ax plus is equal to 0. The only value that will satisfy this equation is all the x's will be 0. Okay, and the solution now, because we are solving this, ax is equal to b, so there will be a unique solution if it exists. So if there is a solution, so it will be a unique solution. Okay, so if ax is equal to b had a solution, so if it exists, because it can either have no solution, or if it exists, if the solution is there, then the solution will be unique. So we can say that if we have rank is equal to n, so the rank is basically equal to the number of columns. So what we can say is about this ax is equal to b, we can say it can either have 0 or 1 solution. So 0 solution, basically if the solution does not exist. So 1 solution, that xp, x special solution will be there. Is it clear?
Sir.
Okay. Okay. I would like to give the examples as well, but I just want you to revise the lecture in the next session. If you are not able to sort of argue this on your own by seeing the examples, then you tell me about that. Okay. Now we can have one more thing. We can have, if this we have r is equal to m, we have this full row rank matrix. So if we now have full row rank matrix, so what is the meaning of that? Basically that means r is equal to m. So if we have an m cross n, so a is equal to m cross n. So in that case, there can be two cases. M can be greater than n, and either it can be less than m. So what I'm saying is r is equal to m. So the pivot rows basically here are, so pivot rows is equal to m. Okay, this is the pivot rows that we have. So this is the rank. So now we want to see, so how many solutions does it have? So the first question that we're trying to answer is, can we solve this ax is equal to b? Can we solve this? And for
Sir, by using the transpose of matrix, maybe.
no, I'm trying to claim any other thing. So I'm saying, for example, if the rank is m now, so rank m means that the pivot rows basically are m. So pivot rows are m. So we have m pivot rows. Okay, now we are trying to argue about this. Where will there be a solution? Will there be infinitely many solutions or things like that? So what I'm saying is, if
Sir,
ax is
if
equal to b,
m is less than n, then it is possible, I think.
if m is less
Less
than
than
n,
n.
so
Yes.
then what is it?
Then it is possible.
Basically, you are saying the number of equations is more than the number of variables, is it?
Sir,
Because we have
because like number of pivot variables should be less than the of number of pivot calls should be less than the number of columns, right? For there to exist solution.
no, pivot column always are less than or equal number of columns. So pivot will be always that, because you are taking pivots from the columns.
Yes, sir. So if m becomes greater than n, then it's not possible because there are m pivot columns, and there will be.
Okay, because that time we cannot, if m becomes greater than r, so it's not possible that we can have rank m. Why? Because I told you the rank is less than equal to minimum of n comma m.
M comma n.
So if m becomes greater, then the rank obviously will be n. Now I'm claiming, this is the first
Yes.
claim, that rank is equal to m. So that basically means that this is some sort of matrix like this, in which m is basically less. So m is less is
Then
some sort of
then
matrix like
solutions
this.
are possible, sir.
Yeah. So it's not just solution. Sometimes solutions may not exist. Sometimes with this setting as well, solutions may not exist. At least you at least understand the argument that I'm making. So I'm telling you that r is equal to m. So this establishes a fact that m is less. So we have this some sort of matrix which is taller matrix. So this has matrix like this, in which we have less number of we have these I think we have m is less than n. So n basically this rows are like this, so this basically should be a matrix which should be wider. So we have 1 2 3 up till m, and then we have n. And we said that m is less than n. M should be less than n because of this, because we established this fact, r is less than or equal to minimum of n and m. So m is less than this, so this basically means that columns will be more. So we'll have a matrix like this, which is a fatter matrix. So we'll be having a lot of columns. So in that case, I'm saying is that if r is equal to m now, so we have what is called as a full row rank matrix. Full row rank matrix. So what I can say is that we have to find the solutions to x is equal to b if it exists, and we'll see where it does not exist, and we have to make the special things. Let's suppose if the solution average exists for this, let's suppose for this b. So what we will do is, so now number of pivot columns is equal to m. Okay, so number of free variables, how many free variables are there now? So if the pivots are m and m is less than n, so if the number of pivot columns is m,
n minus m.
right, so n minus m. Okay, n minus m, or I can write n minus r, because this is the rank. So these many free variables will be there, or n minus m or n minus r. Let's again write that to not confuse you guys. Okay, let's take an example. Let's suppose a is like this. A is 1 2 6 5. Okay, then we have 3 3 1 1 1, something like this. This is the matrix. Okay, so what you can say about this row reduced echelon form? How can you make the row reduced echelon form out of this? Okay, you know that you'll have to make this entry as 0. Okay, you'll have to make this entry as 0, this circular entry which I made in the circle. So now how to make this 0 is like this. So it will becomes 1 0. Let's suppose I'm multiplying with this 3. Let's suppose something will happen and it will be 1 0 0 1 if you have something, so it will be like a b c d, something like this. This is some other value. Let's suppose 5 value was here. So what I'm saying is that this matrix, row reduced matrix form, will look like this after you reduce this, because you now know the element transform, how to perform this element transformations. So you will get an identity over this, and you will get some values f over here when you perform this row reduced echelon form. Okay, I'll call this f. Now you see this. Okay, so this is what we got out of this. So this is what we got. So if you now have to find the solution, so what will be the solution of this? So it's easy if you want to find the solutions. So this, if you have sort of watched previous lecture, so we directly told that we will get this if, and this negative f will be the solution. Okay, if the solution exists, so this will be the solution directly if you see that. Okay, is it clear?
Yes, sir.
This is for the case where m is, and if we have what is called as full rank matrix, where it is a square matrix, the best case that we can get is rank can be equal to m is equal to n. So the first thing is that it will be a square matrix. Let's suppose this is equal to a is 1 3 2 1, something like this. If we have a matrix like this, so you know that this row reduced echelon form will be I directly. Do you agree with this? Row reduced echelon form will become 1, because all the columns will be basically pivot columns. So pivot columns, these pivot entries will become 1, and other entries above below that we want to make them 0. So do you agree with this, that row reduced echelon form will become I matrix?
So
Yes,
it
sir.
can be also in the form of four matrices within the matrix, right? Like A, B, and in the next column C, D, where A is like identity and matrix and rest
No,
are.
didn't get you. Come up again.
Sir, it can be like, sir, maybe it's not reducible to I,
It is. It
then
will
what?
already reduce, because that's what I'm claiming here. See this. Rank is equal to m is equal to n.
Okay, sir.
So if you are going to this, for example, this is I told you that this is a m cross n matrix. So maybe if it is if there was like p cross q. So I got your point. What you wanted to tell. Maybe you are telling like this. So if we have a bigger matrix p cross q, and we have a small scalar matrix inside that, which was m cross n. Is that what you were referring to?
No, sir, no, I got it, sir. Like pivot is M is equal to N, so
Ha ha ha.
like I understood, sir.
Right, right, right. So for that, you will easily get this row reduced echelon form is equal to I if you see this. So now if you want to find the solution, so ax is equal to b. So ax is equal to b will be able to solve this. So again, I want to again just make these things clear. So here there will be a unique solution again. There will be a unique solution. Why? These will be the solution. So when you will get this, there will be only one solution which will satisfy the equation. So the three cases basically are where r is equal to m is equal to n. That's the first case that we have. So here we'll have one solution. Try to argue it when you spend time with the lecture. Just pause the lecture over there and then try to argue it mathematically and try to get some intuition. So if r is equal to m is equal to n, because we know the row reduced echelon form will become identity. So how is this the how will we get the only only unique solution? Try to argue these things, because I don't want to give you everything. That basically becomes spoon feeding then. So you'll have to think, you'll have to sort of put more efforts into this in order to understand these things fully. Then I told you that if r is equal to m, where m is less than n, that's the other case. So in that I said you that r becomes something identity, and in the like below this there is 0, then it has 0 or 1 solution, if this is the case. And what is the third case? If r is equal to n is less than m. So if rank is equal to number of the pivot, that's the first case that we handled. So in that we had r is equal to if. Okay, so that was the case we handled, and we saw that there can be basically infinity solutions, like because of the free variables, infinity solutions. Okay, so there can be one infinite, but basically one, and you can take the combination of that, and it will become it will be basically one and infinite solutions, and or not even even I told you that there can be, if it exists, so that means zero solutions as well. Yes, so zero or infinity. So if the solution does not exist in the first place, so there will be zero solutions. So otherwise, if they exist, there will be infinite solutions. Okay. So you'll have to argue these. This is the whole thing that I want you to like sort of have in your mind. The first thing is that if rank is equal m is equal to n, that's the last case, there will be a unique solution. Okay, and if rank is equal to m, that is less than n, there will be the formula of this. It will be, if the solution exists, there will be only unique solution. And if rank is equal to number of columns n, then we will have, if it exists, then we will have infinite solutions. So if you this thing can be achieved from these two things. This first case can be achieved from these two things, if you see it. So why? Because here we are saying is if it's m, then it will be having 0 or 1 solution. That is, there will be unique solution. So in this case r, where is and we are saying it will have 0 or infinity solution. So we are saying here it is m is equal to n, both of the things. So there will be only one solution that will be unique if it exists. So there will be unique solution. Okay, I think like you have to sort of revise these things to get a hang of these things. So but that's the thing I want you to at least have in your mind regarding the rank. Okay, is it clear?
Yes, sir.
Okay. Now we'll go on to this. I think we have covered this independence vectors, and we have covered this basis and dimensions. So what are dimensions? So I'll just ask you a question. If I found that you don't understand, maybe I'll take the dimensions also. So what is the meaning of a dimension? Okay, first let me tell what basis is. So what are bases? I think I explained it multiple times what bases are. So what are bases? What are basis vectors basically? So whole of this lecture basically went to revision. Otherwise, I thought I'll cover this whole thing in 15 minutes. So what are basis vectors? Amir, can you give the answer? What are basis vectors?
Yes, sir. Sir, bases are actually points from which we can span the whole matrix.
Whole
Whole.
vector space, right? You have a
Yes, sir.
brief idea, right? So bases basically are the set of vectors. So first, I told you about the spanning. What is spanning? So if we have a vector v1 and if we have a vector v2, so if you take all the linear combination of these vectors, you will be able to reach some vectors. So all these vectors, for example, let's suppose we are having some vectors, v1 will be reached, v2 will be reached, and then addition of the, and there will be a lot of vectors. So a bunch of vectors will be there, which will be reachable by v1 and v2. So this is called as span. So span means what are the vectors that are reachable by the linear combination of these vectors. So if we have the if we have v2 and v2 v1 and v2 vectors, so we'll be telling you that the linear combination of these v1 and v2 basically is span. So now what I am saying, if there is a vector space, if there is a vector, you now know that what vector space is. If we have a vector space, let's say we call it a v, vector space is v. So in that way, I'm saying you, what is the basis for this v? The basis means, so this vector space, maybe there will be a huge lot of vectors. Let's say R2. So in R2 we have the whole 2D plane. That is our vector space. Okay. If I tell you that what are the vectors that will span this? So you can tell that the vectors 1 2 2 4 1 2 2 3, let's suppose some random two vectors, so they basically can span this whole vector. Okay, this can span. So other vectors that can span 1 2 9 8 6 1, they also can span. So if you should see, these three vectors can also span. But what is the minimum number of vectors that are required for the spanning of this whole R2? So you can see that it is 2. Okay, so here the vectors in which we have this minimal spanning set, minimal spanning set, this is called as basis. So basis basically have two properties. The basis, what is basis first? So bases are the vectors which can span the whole vector space, and the property should be, it should be minimal spanning set, minimal spanning set. And the second property is that it should be maximal, or I can say maximal independent set, independent set. What is the meaning of this? Meaning of this is, let's suppose we have this vector 1 2, we have this vector 3 8. So I told you this can be basis for R2, these things. So if I add one more vector into this, let's suppose 9 and 2, so what I'm saying is this still can span the whole vector space, but these two are enough to get this vector. So you see this, that this vector is linearly dependent over these two vectors. So this set of vectors is basically linearly dependent. So by linear dependence I meant that, so if we have vectors, bunch of vectors v1 v2 till vn, so the meaning of this was, so if one vector can, or if some vectors can, we can achieve these vectors by taking the combination of other vectors. So mathematically how I wrote it, I said that c1 v1 plus c2 v2 and so on till cn vn is equal to 0 only if all of these coefficients are 0. So this thing will become 0 only if ci becomes 0, if every coefficient becomes 0. Otherwise, if some coefficient becomes non-zero, that means you can combine the other vectors to get that one, to get that vector. So it is a linear dependence. So what I'm saying is, here is minimal independent set. So that means that the vectors should be independent. If you just add one more vector in that vector space, so you can get that by the other two vectors. So it will make the whole vectors as dependent. So I'm saying minimal spanning set, it should be, number of vectors should be minimum and they should span whole the vector space. And it should be maximal independent set. That is, if you add one more vector to that basis, so then the whole of this becomes dependent. So it won't remain the basis. That's the concept of basis. So from basis basically means, if you have vector space, the basis for that are the vectors by which you can span whole of the vector space. That was the concept of basis. So if you just see this R2, it has 0 1 and 1 0. These are standard bases. So some other vectors can be also there. Some other vectors, like just I took 4 5 6 9. This also can be a basis, but these are standard bases. So one thing that is common in all the bases is that number of vectors in basis is equal to 2 in this R2. So what I'm saying is that number of, if you take basis vectors for any vector space, there can be infinitely many bases. There can be infinitely many combinations of vectors which can be candidate for the basis. Now I'm saying that the one property that is common in all of these bases is that the number of vectors in each of the bases is same. So in this R2 we have this 2. This is what we call as dimension. So the dimension mathematically basically means the number of vectors that are required to span whole of the vector, the minimum number of vectors. In the basis, there will be minimum spanning set. The number of vectors that are present in the basis is called as dimension. Is it clear?
So,
So every basis vector, just remember this point, every basis for a vector space has same number of vectors in it. That's why bases there can be infinitely many bases. So here in this 0 1 1 0, that's called standard basis. So if we have R3 basically means the three-dimensional plane, the three-dimensional space that is like this. So we have some axis like this, and it will form some, let's say, that cuboid sort of thing. So in R3 we have standard bases as 1 0 0, comma 0 1 0 and 0 0 1. So these are our standard bases. That's still a base, and there will be other candidates for bases, but the common thing is that there are same number of vectors in each basis. Whatever basis you choose, there are same number of vectors. Okay, and that's how we define the dimension of the vector. How we define the dimension of the vector space. So dimension of the vector space basically is the number of vectors present in basis. So now I'll also write dimension of a vector space. So it is number of vectors present in basis of vector space, in basis of the vector space. Is it good? Are you understanding this now? Let's suppose we have a matrix. Let's suppose we have, what matrix can I take? Let's suppose we have a matrix 1 2, maybe I'll make some 2 1 2 3 2 3 1 1 1. So let's suppose this is my matrix. Okay, so how to define the column space of this matrix? So how to define column space? So column space, basically I meant by column space is take linear combination of all the columns of this. Okay, so take the linear combination, obviously 2 1 2, it will be in the column space, because you will take 0 of this, 1 of this, 0 of this, 0 of this, so that will be this 2 2 1 2. So if I want to take 5 3 and 5, so what combination of these vectors should I take so that I'll reach 5 3 5? Can you give me like what combination of these vectors can I take to reach this vector 5 3 5?
Sir, column 1 should be 0, column 2 should be 1, column 3 should be 1, column 4 should be 0.
Right. So this is what I want to get. So I'll take 0 of this, 1 of this, 1 of this, and 0 of this in order to get this. Okay. So all these vectors which can be reachable by taking the combination of these is called a column space. Okay. It's not that difficult. The only thing why it becomes difficult is because either the terminology may be new to you, or the other thing is you may not have heard revised it enough. That's the thing. So what I'm saying is column space is take the linear combination of these and you will get the column space. Okay. And even what is null space now? Again, taking this matrix. So this was column space of A. So if I want to take null space, null of A. So what I'm saying, you give me the combination of these rows so that it would take this to 0. So now here we have in the column space, we see the output, output vectors. In here, I want to get the input vectors, which will give the value 0 0 0. So if somebody tells you like is 5 3 and 5 in the column space, yes it is. Why? Because I can take linear combination to reach this. So now I'm saying you that the question is I have to reach 0 0 0. So can you give me some bunch of vectors? Let's suppose one vector at least, by the help of which I can reach the 0 0 0. So the one obvious will be take 0 of this, 0 of this, 0 of this, 0 of this. So 0 0 0, it will be always in the null space, this vector. Now what I'm saying is other thing is, so if I let's suppose take -1 of the first and +1 of the last and 0 0 of this. So I'm taking this one time -1 times and this 1 time. So if you add these two things, it will become 0, isn't it? And if you take 0 of these two, it will become 0. So the one vector I wrote is 0 0 0. That was one present in null space. Then -1 0 0 1. So what is the other vector? Let's just practice with other vector. So what vector can you take so that the combination becomes 0? Okay, what other vector can you take? Can I do one? This 2 plus 1 is 3. This 1 plus 2 is 2. This 2 plus 1 is 3. So can I take 1 times this, 1 times this, -1 times this, and 0? Riyan, Salim, Amir, are you understanding this? So this vector also.
Yes, sir.
This vector 1 1 1 -1 0. It also is in the null space. So there will be a bunch of vectors. And we saw how to find the whole null space by using that row reduced echelon form. That's what I meant by the null space. Okay. So now I want to say, and as you know, this column space and this null space, it is a vector space. Okay. I need to find the basis of this and the rank of this. And how to do that? How to do that again? So if I want to find the null space of A and we have column space of A, if I want to find the, let's suppose rank of A. What is the rank of A? So I said rank of A basically is the number of pivots. So how to compute this rank? Just reduce this matrix into row reduced echelon form, and then you will get two types of columns. One will be pivot columns, other will be non-pivot column or free variables or free columns. So the number of pivot columns will give you the rank. Is it clear?
Yes, sir.
So what do you think? So this matrix, let me write it again over here. So we have a matrix 1 1 1 2 1 2 3 2 1 1 1 1. So what I'm saying is that this entry will become the first entry. This will become pivot. Okay, and now this entry also will become pivot. Other entries will become 0. These entries will become 0. So this will get reduced to some 1 0 0 1 something like this, and some values over here. So now you saw that other pivot also became 0. So here we have two pivot variables. The rank of this matrix will be 2, but you have to reduce it in the row reduced echelon form. I'm just guessing that, not even guessing, like I'm certain that this will happen here. So but you have to get thorough practice so that you see it without even solving it, without even getting the row reduced echelon form. And here row reduced echelon form will be of this format. Like in your spare time, just pause the video and find this row reduced echelon form of this, and you will land up like this. You'll have two pivot columns, and other two will be free columns. Is it clear? So for this we can say rank is 2, because number of pivot columns is equal to 2. Okay.
Yes, sir.
So these pivot columns can also serve as bases, because if you know that by only having these two vectors, I can reach this vector, because I will just add these vectors. I can reach this vector by taking one combination. So you can see that the basis vector here, I can write basis vector 1 1 1 is one vector, and 2 1 2. This is the basis vector for this matrix. Okay, if you see this, these two columns I can take as basis, because I can reach this matrix, I can reach this as well. So I can reach any of the values that is reachable for the whole matrix. So I can see that the basis basically now has two what I can say, two independent columns. So now the dimension also is equal to 1. Dimension is equal to 2 for the column space. So if I say column space of A, so now we have n of A was our null space. It had rank 2. Null space had rank 2. Why? Because if in order to get this, in order to get any of these vectors, so I have, because I have these two free variables and I have two pivots, so I can get anything from the null space. So I'm saying you that there are 2 is the number of 2 is the rank for this rank of this matrix, and 2 is also basically the number of pivot columns, and this is also equal to dimension. If you see, you can formally prove all these things. I'm just taking an example and then showing you all the properties over here. By taking this matrix, I saw that if I take the matrix number of columns, number of pivot columns is 2, that means rank is 2, rank of this A is 2. If I have to take this n of A, I have to see what is the dimension of that. I have to again see the dimension of column of A and things like that. So I'm just giving examples. So there are formal proofs which we can do mathematically. Is it okay now? By just seeing the example, I don't want to formally prove all this, because that requires a lot of mathematics. Is it
Sir.
okay? So now as I also showed you that column space of A has these two bases. So the dimension of column space is 2. I think we still have some time left, so we can see it. So what I can tell you is that dimension of column space of A is basically equal to rank. Can I establish this? So from this matrix, if you see this matrix again, this is the matrix we had: 1 1 1 2 3 2, and we had 3 4 3, and then 1 1 1. This is the matrix we had. This is the matrix. So what I'm saying is, I said the rank of this matrix basically is the number of pivot columns. So pivot columns were first and second. This was the pivot column we had, that is 2. So in the column space of A, so column space is basically take any linear combination of these and you will get the basically some vectors, and all these vectors will be the column space of A. So but I know that this 1 1 1 vector and this 2 3 2 vector, by using only these two vectors, I can reach every vector that is reached by this whole matrix. So I can say that these two vectors are bases. I can say these two vectors are bases of column space of A. Okay. Now the basis is column space of A. Now you know that the number of vectors in basis is equal to dimension. So dimension is basically 2. The dimension of the column space, dimension of column space is equal to 2 now. That is equal to rank. That is equal to the rank. Can I claim this from this example, from the above example?
Yes, sir.
Rian, can I claim this?
Yes, sir.
So I can claim this from the example, but in order to prove these things, you have to formally prove. But I'm just claiming it based on this example. But this actually exists, and this is true for every matrix. I'm just taking the example so as to convince you, because I don't think proofs are necessary. Because without proofs, you can still understand the things. But proofs are a really good thing. If you are maths major and if you want to like really excel in maths, then you have to give proofs and you have to take a general example and then maybe give the proof. So from this example, you can see that Dimension of column space of A is 2, which is equal to rank. Okay. In the similar way, now we have this null space of A, which I said n of A. So the dimension basically will depend on the free columns there. So you saw that how did we compute those null space of A? How did we compute the number of free whales? We assigned them values and we do the linear combination. So that dimension of null space of A will basically be equal to number of free columns. So how many number of free columns will be there? If this is rank is equal to R, so it will be, if this is equal to R, so what will be the dimension of a null space of A?
Column number minus R.
So the total number of columns, so that was n that we took and minus R. So these are the dimensions for this column space and dimensions for null space. I'm just giving you some intuition. Maybe take some time to formally prove it. If you want to like really understand these things, just take some time. Without this single matrix, you can take a general matrix and then try to prove these properties. But as I said, this proofs are unnecessary. The thing that necessary thing is you should visualize things. You should visualize the thing, and the other thing is you should get the intuition based on the visualization, and you should know the facts, know these things. This is what, at least for these two things, I now established two things. I said that we have dimension of column space that is equal to the rank, and that's R, and the dimension of null space of A that is equal to n minus R, because that's based on the number of free columns. Okay, is it enough? So is it do you understood this? So if you understood, then
Yes,
I
sir.
can move to the fundamental subspaces. Now you saw two subspaces. Okay, it will be a full, let's take a 2-3 minute break. I'll also get some water. Maybe I'll pause the recording as well. Take some breath. How to pause? I don't know how to pause the recording though. Let me find some shortcut if there is. Yes, there is a pause button. Okay, coming back off the break. So what I'm saying is that we saw two subspaces. So if there is a vector space, so what I told you that in vector space we saw a concept of subspaces. So we saw two subspaces. The first subspace that we saw is column space. Column space. We represent that by C of A. And the second thing that we went through is null space. Null space, that is n of A. Okay, we have other two subspaces as well. Don't be scary, but we have covered everything. So the third subspace there is, it is called as row space. Now we have this matrix. If you again see this matrix, in that we had columns and rows. If we take combination of the columns, we call it a column space. If we now take the combination of rows, you know how to take combination of rows. So if you have row 1, row 2, row 3, and you want to take some combination, so it will be 1, 2, 3, 1 times this row, 2 times this row, and 3 times this row. So this will be called as the row space of R of A, row space of A. Okay, this is the combination of rows basically. Okay, and even you can transpose a matrix. So you can say it is column space of A transpose. Do you agree with this? It's column space of A transpose. If you just transpose A matrix, it will basically, the rows will be converted into columns. So now it is a column space of this. So the fourth is what we call as, I think, left null space, we name it. We call it null space of A transpose, or we call it left null space. And I'll show you why it's called left null space. So it will be null space of A transpose. These are the only four things that I want you to remember. There are four these are called fundamental subspaces. They are sometimes called as four fundamental subspaces. These are four fundamental subspaces. Okay. So one is the column space that we read in detail. Null space, we also have detailed discussion over these things. And again, you have to transpose these things to get the row space and the null space. Is it clear? Are these four names at least clear by now? Now we'll see one more thing. We'll see what is the dimension. Let's suppose we have this matrix A that is having, I am using the dimension interchangeable. Dimension, I mean the number of columns and rows, but the formal mathematical dimension, my definition is that the number of vectors in the basis. So I think the context is pretty clear. When I speak dimensions in the basis concept, it is the number of vectors in there. When I speak dimensions in terms of matrix, so I'm saying number of rows into columns. So let's suppose we have this matrix in which the matrix size is m cross n. Okay, let us say this is. So now you know that this is m cross n. So what is the column space lies in? So what is the dimension of column space? So what is the vector space of this column represent? So here, if you see every vector, it will be in Rm. It will be in Rm. Why is that? Because here we have m rows, 1, 2, 3, 4, like this. So we are multiplying it with something to get column space of A. This is our A. We're trying to get this column space. So we are taking the linear combination of these columns. So we are taking linear combination of columns, basically one column, second column, third column. So the entries in here in the column space will be basically the number of rows in here. Did you get it? The column space of A, the vector size will there be dependent on the number of rows in this, because we are taking the combination of these things, the combination of columns. Again, to reiterate it, just see it. So we had these columns, we had these entries. So we want to take linear combination of this plus or minus something, this, some this. So if you see the resultant vector, that will have this entry, some entries, this entry, this entry. So the number of rows. That's why I'm saying these vectors belong to Rm. Is it justified? Is it clear? I don't think it requires a proof. It's pretty clear.
Yes, sir.
Rian, are you clear with this? How does this column space, vectors in column space belong to Rm?
Yes, sir.
Right. So what about null space now? So null space basically says you, let's suppose we have this matrix in which the entries were like this. It says you how many, what is the combination of vectors that gives you the zero vector. Okay, that gives you the zero. In this, what we again do is we take some linear combination of this, plus this plus this plus this. So in that you will see that what will happen is, so if you have, let's suppose only we have x1 and x2, let's suppose x1 and x2. So why? Let's suppose we have this, the number of columns is this. So we are taking 1 times of this and 1 times of this. So you might see the equations in here can be more. There can be, like, for example, 10 values in this, 10 rows can be there, but there are only 2 variables, that's the columns are only 2. So the value that we'll get basically here, the value that will, the number of 0 will get 0 0. So this will basically be the number of columns that we have, Rn. These values will basically belong to Rm, because this is the value of Rm. Column space will be this. So you have here 0 0 and so on. So the value will belong based on the number of unknowns. Because if you see this, these things will become the null space. So the number of unknowns we have will become basically this. So number of unknowns depends on the number of columns. If you see this matrix Ax is equal to B, where this x came from? The unknowns. So this is where the vectors in the of the null space will lie. That's what I have written here. So the null space will lie in Rn. Sorry, it should be Rn. Is this clear? Why does this lie in Rn?
Yes, sir.
Okay. So again, the similar thing, similar story for the, because they are just transpose. So here, what can you say about the transpose? And what can you say about this? So just flip these values. So flip this, so it becomes an n, m cross n. So it will be Rn. So here it will be Rm, because they are just flipped versions. So there you are just flipping the matrix. So here we saw that what is the output, sort of where do they lie? If they have, if we have a real number, space of real numbers, where are these things lying? Is it clear? So how to make this? There's a beautiful picture actually made by, I think it was initially introduced by Gilbert Strang from MIT. So he introduced this, and please remember this picture. Now we have these 4 subspaces. Everything that we will go into this linear regression where we'll be going the algorithm, I'll be just calling this. I'll be telling a C of A, we have this column space, we have this row space, we have the left node null space, we have the left null space. So remember these 4 figures. So what we have is, if my art does not become a constraint, let's be a little bit artistic. So this, okay, and let me make it a little better. I can do better than this. Even I can do better than this. I think justifies. So what I'll say, Rn. As you see in Rn, which of the things belong in Rn? If you see this null space and row space, they belong to Rn. So I can write null space over here, null space, and what is the other thing that belong to Rn? Row space. Well, let's write row space at the top. Row space and null space. Okay, both of these belong to Rm. That's why I just clubbed them together. And this picture is really important. Why is it important? I'll tell you when we'll be going on the orthogonality projections and things like that. It became a little bit bigger. No, cannot draw the perfect pictures. Okay, so now we have this Rm. Let's call this Rm. What are the things that belong to this Rm? So we have this column space that belongs to Rm and the left and null space of At. So we'll write column space at the top, column space, and at the bottom we had left null space or null space of A transpose. Here is null space of A, n of A. This is n of A transpose. Okay. Now let's see. We'll compute the bases and dimensions. Bases and dimensions. That's what we are trying to formulate. As you saw in the previous session, not in the previous session, in just the previous, I think 10-15 minutes ago, you just saw we computed the dimensions and the rank for this. If you just go over here, you saw this dimension of n of A, dimension of C of A. We saw this. Okay, and you have to again, if you just forgot it, just go through it again and to see how we arrived at this. Okay, so number of pivot columns basically gives us this column space of A, and number of free basically gives the null space of A. So that is R and n minus R. So in the row space basically means this R of this one. If you again see this, if I want to compute the dimensions, so you'll have to go this. So dimension basically is R now. So dimensions is equal to R for which one? As you might have seen that, the column space of A. That is here. I have written it. Where was it? Here. If you see dimension is 2, dimension is basically R. So dimension of n of A is n minus R. Dimension of n of A is n minus R. So here we have n minus R. So here we have R. Okay. So if you again see this row, so this row will have the dimension of the row space will have the dimension of R. This thing. It will have the dimension of R because it's again the rows basically you have to take the linear combination. So here it will be m minus R. This is the dimension. So I'll write dimension with, let's suppose, some yellow symbol. So this is R n minus R, n minus R, and this is m minus R, and this is again R. Okay, because you know that the similarity between row space, I just told you how to why is this dimension of column space is R. The dimension of column space R because this is the number of pivot columns that we have. That's where we got this R from. And now for this null space, what we saw is that number of free variables. The number of free variables were n minus R. That's where we got these values from. And if you see, this is just flipped of this. So if you see AT, so AT is just the transpose of this. So that's the same dimension will be there, but the dimension will get changed because now the columns will be, now this rows will be there, m minus R. And similarly for this row space, nothing got changed basically. So here this row space will be again the pivots. So number of pivots basically. That's why this is how we define the dimension. Is it clear? Are the dimensions clear?
Yes, sir.
Rian, is it clear? Because I have explained you that how do we get dimensions of R and n minus R. I think it is pretty straightforward to get this transpose wala thing.
Yes, sir.
Okay, nice. So let's now move on, and why are we like giving this much of seriousness onto these subspaces, and what is so special about these things? Okay, so that we have to take care of these things. Should we even take an example? If I can do an example so as to sort of give you this. So what I'm saying, let me first tell an example because there are some important properties that I wanted to tell you about. Let's suppose I'll take the same example that I have been doing so far. 1 1 1, and then we had that 2, and then I think it was 3. It was 2 2 1. I think this was 3 2 1 2, huh? So because we added these two columns that time, so this is 3 2, and this is 3 3 2 3 and 1 1 1. So this is what we had in the initial matrix. So when I try to get and row reduce echelon form of this, so what I told you is that the first this column will become, so this will be a pivot entry, this will be a pivot entry, and others will get 0. So we'll get something like this: 1 0 1 1, and something like 0 0 0, and some f over here, something. Let's actually solve this so that you will also get a practice of row reduce echelon form. So maybe this will be the last topic, and then we'll be subsequently doing it. So how to do this? So I'll just subtract the first equation from both of these. I'll subtract first equation from both of these equations. So it will become 1 2 3 1 will remain as it is. So then this will become 0, this will become 0, 1 minus 2 will become minus 1. So 2 minus 3 again become minus 1, 1 minus 1 will become 0, 2 minus 2 will become 0, 3 minus 3 0, 1 minus 1 0. Okay, now I can do one thing. I can just divide the second row by minus 1. So I'll get 1, I'll get 1. Okay, so this is the final matrix that I'll get. Just erase this one now. So this is the matrix I got. Again, I can do one more operation. I can just subtract the equation from row 1. So I can just multiply this equation by 2 times and then subtract it from row 1. So 1 minus 0 is 1, 2 minus 2 is again struck off this, it will become 0, and 3 minus 2 is 1, so this will be 1, so this will be 1. So this is what we got after the row reduced echelon form. So the final matrix we got is 1 0 1 1 0 1 1 0 0 0 0 0. Were you able to follow this, like how I did it? Were you able to follow it? Nice.
Yes,
So
sir.
this is the row reduced echelon form of the equation of this matrix. This is what we got. So if you see column space of A, if you see the column space of A now, okay, if you see the column space of A, because I operated on the rows, now the column space got changed. So column space did not, because you see this no, I operated on the row space. I can say how can I, column space of rows, or maybe span of rows, what I can say it. So we had this column space of A. So the column space of A was basically whatever I can reach up to the columns. So I still think the span of this column space is same. So because how I got this, for example, if I need to get 1 1 1, so I'll just add this and this, I'll get 1 1 1, I'll get this out of this. If I need get 2 1 2, so I'll multiply this with 2 times 2 1 and 2, and 2 1 2. Is 2 1 2 possible? So that means the column space has not remained same, right? So we establish column space has not remained same. Column space has not remained same. Because now initially I was able to get, for example, let's suppose I was able to get this 2 1 2 in the column space. Now that you performed the rows, you did row operations. Now you are not able, because this is the matrix that got changed. And the column space has not remained as it is. But I think it should remain as it is. Is it? Have we done something wrong? Or should it not? It'll remain as it is for ax is equal to 0, but this is ax is equal to b. Okay, so what I can say is that initially we had in column space we had this 2 1 2. After making it in the row reduced echelon form, we are not able to get this 2 1 2. Are you clear with this? So do you agree with this point? So how many of you
Yes, sir.
agree with this point? I think yeah, column space has got changed, so column space has not remained the same. Because initially in the column space we had, let's suppose this 3 2 3 vector. So now from these columns you cannot reach 3 2 3 vector, because whole of this became 0 basically. Is it clear, Rian? Are you okay with this? Column space has not remained the same because it got changed. Now I'll say that row space has not changed. So row space of A, which we'll call C of A or C of R, row space basically, it basically remained the same, because I was able to get initially 1 2 3 1. So I'll be getting that 1 2 3 1. So multiply this with 1, and multiply, for example, this with I'll get, sorry, so I want to get 1 2 3 1. So I'll get 1 from this, 2 from this. So I'll just yes. So yeah, I can get that. So this remains same. Remains same. Well, how? So how to basically reach whatever operations I performed on this to get into row reduced echelon form, I'll just perform the reverse operations in order to get this. In order to get the row space, and we have denoted that, let's suppose row space R of A. So row space basically remained as it is. Why? Because if you perform the operations in reverse, so you perform certain operations in order to go from here to here, in order to go from here to here. So if you perform those in reverse, you'll be easily able to get these operations because these element transformations are reversible. So I'm saying the column space has not remained as it is, but the row space has remained as it is. Am I clear with this?
Yes, sir.
Yes, sir.
So why has row space remained as it is? Because if you take the matrix and you perform certain operations, and you can just roll back these operations, you can just go back and you can see that. Okay, I think this is clear now. I think we should stop it here, and we'll sort of continue this lecture from the subspaces. At least I'll just summarize whatever we did. We had these 4 subspaces: row space, and we had this row space, we had this null space of A, and we had this column space, we had null space of A transpose. The first property that I saw that I showed you is that the column space has not remained the same. It has basically changed because we performed certain operations on the rows, and the whole columns got changed, and we cannot reach some vectors which we were able to reach in the initial phase. But this row space has not got changed. Why? We will be able to sort of roll back it if we perform certain operations in order to get to this row reduced echelon form. If we again undo this, because element transformation, they are reversible operations. So if we can reverse this, we can go back to this. So these are the fundamental 4 subspaces, and the dimensions are also mentioned in here. So you can just sort of brainstorm these things, and then put a little brain and put a little efforts to understand these things, and then you can establish these things. Is it okay? Can I stop the lecture and
Yes,
I
sir.
may take some questions from you? So where is it?